All right, well, it is noon, and welcome everybody to another Iowa Learning Farms webinar. My name is Mitch Harding, and I am a water outreach specialist with Iowa Learning Farms. And today we're going to hear from Stephen Hall, Assistant Professor and Extension Specialist at the University of Wisconsin-Madison, and he's going to discuss a virtuous cycle of soil organic matter and diversified cropping systems. So throughout the presentation, if you have any questions, feel free to go ahead and put those in the chat, and we'll get to those questions at the end of the presentation. So without further ado, I'm going to pass it on over to Stephen.
All right. Well, great. Well, thanks, Mitch, and thanks to you all for attending this afternoon. So the title here is a little bit tongue in cheek. The meaning will hopefully become apparent as we go through the talk. So many of you are familiar with this broader context of agricultural management as a climate solution, right? And so now we have billions of dollars in funding that's flowing both from the federal government and from various private sector entities aimed at incentivizing climate smart practices that purport to sequester carbon in agricultural soils and to decrease overall greenhouse gas emissions from our systems. And I think there's tremendous opportunity here, a lot of excitement, and I think, as always, we need to bound our expectations with sound science. And this is a really useful table prepared by some of my colleagues at Iowa State, describing some of the various market-based initiatives that are incentivizing carbon storage or greenhouse gas emissions reduction practices. So each one of these columns is a different one of these programs, and you can see some common themes emerging, right? Essentially, all of these programs incentivize cover crops and no-till practices. And indeed, there's some good evidence that, in many cases, we can store some additional carbon in soil organic matter by adopting these practices. What's also interesting is that many of these programs also incentivize changes in crop rotations. And so diversified crop rotations, increasing biodiversity, shifting from annuals to perennials, et cetera. And I think this is a really interesting and powerful opportunity, but I think, as with everything, we need to be careful about evaluating both the size of the climate benefit that we might get and the mechanisms through which those benefits arise. And I think from we know that carbon cycling in soils is really complicated, but at the end it boils down to two processes, right? So inputs of carbon from plant detritus, both from the shoots and the roots, and then the decomposition of carbon back to the atmosphere as CO2. And the key point, right, is that many of the practices that we are incentivizing with under these various programs can affect either one or both of these arrows, right? We might have greater carbon inputs to the system and or changes in decomposition. So we have to keep our eye out for interesting dynamics that can arise. So for today's discussion, I'm going to leverage some data from projects that I was working on when I was at Iowa State University with a number of different collaborators. In particular, we're going to look at how two diversified systems, so a crop rotation system and a system with perennials, affect the storage of carbon and organic matter, but also the amount of nitrogen fertilizer that's required for these systems, and knock-on benefits for climate and water quality. And so these two long-term experiments are the Marsden Farm Cropping Systems Experiment and the Comparison of Biofuel Systems, or COBS experiment. Many of the folks listening may be familiar with these studies. So I'm lucky enough to be able to present some new data today, but this is really a much larger collaborative effort. I'd like to thank in particular Matt Lieben, who started the Marsden Farm experiment and was one of the main PIs of the COBS experiment, as well as Wenjin Huang and Bo Yi, who were both scientists that I worked with at Iowa State. I'd also like to thank a number of funders, including USDA NIFA, who funded the most recent work that I'll talk about today. So for those of you that aren't familiar, the Marsden Farms Cropping System Experiment compares three different rotations. So sort of a 2-year traditional corn-soybean rotation that's emblematic of what's very common throughout the Midwestern U.S., as well as extended rotations where, following soybean, we have a year of oat and red clover, or 2 years of oat, in alfalfa, and then a second year of alfalfa. And in case you're interested in more details about this experiment, Matt Liebman gave a nice Iowa Learning Farms presentation on this topic a couple of years ago. So one unique aspect of this experiment is that it's been going on for almost or more than 20 years at this point. And so we were able to sample soils fairly comprehensively in 2021 for the data that I'll share today. Another really useful aspect of this experiment is that all phases of these crop rotations are present each year and they're replicated fourfold. So it's a really rigorous opportunity to examine the impacts of these cropping systems on soil processes. So one of the key differences in these rotations is the nitrogen management. And so this is a figure showing those differences. In the corn soybean rotation, we have fairly conventional nitrogen management with a fairly substantial pre-plant synthetic N application and then a side dress. In the 3 and the 4 year rotations, much of the nitrogen is coming from a fall addition of composted manure prior to corn production, and then a side dress application in the corn growing season. The size of this side dress is governed by the late spring soil nitrate test, right? So depending on how much nitrate is measured in the soil, this determines if and how much side dress fertilizer is added to the system. And the key point, right, if we average over all phases of these rotations, the diversified systems had about 75 to 85% lower inputs of synthetic nitrogen. And so we'll come back to this later because it's important when we're thinking about overall impacts for climate and water quality. And again, this is just reiterating some of the previous work by Liebman and colleagues at this site. Both the corn and the soybean yields from these extended rotations tend to be a little bit higher, as you might expect. And then the overall profitability, when you consider differences in input costs and revenues, are about the same among the rotations. Again, I won't dwell on these details, but feel free to see some of the previous studies at Marsden for more context. So again, here we're going to focus more on the soil carbon and nitrogen. And one interesting aspect of these systems is that the 2-year rotations actually seems to have slightly higher overall carbon inputs to the system. And this is maybe intuitively makes sense when we think about how productive corn is in terms of the above ground stover. However, if we compare these rotations, a slightly greater fraction of the carbon that's produced by the plants is allocated below ground as roots. And these are some findings by Hannah Poffenbarger and colleagues, right? So in these diversified systems, more root biomass allocated below ground. In principle, this might help us gain a little bit of carbon in these systems. Okay, so now I'll show you some of our data from our intensive soil sampling in fall of 2021. We collected cores to 1 meter depth in all of these plots, 3 reps per plot. It's necessary to do this deep sampling for carbon accounting because a lot of the interesting dynamics may happen at intermediate depths, right? Not just in the soil surface, but we know these plants are deeply rooting, especially alfalfa. So we want to be able to pick up the changes that we might see along the soil profile. Another important aspect in this experiment is that there is a fair amount of inorganic carbon in the soils present as carbonate minerals. And so we had to account for this in our calculations. So what we found was fairly interesting. If we look at the carbon stocks across all of these rotations, including all of the phases, we see no difference between the 2 and the 3 and the 4 year rotations. And the error bars are pretty small, right? This isn't likely just to be an artifact of measurement. And on average, actually, the carbon was a little bit lower in the 4 year rotation relative to the 2 year rotation. So what about nitrogen, right? So similarly, there's a lot of nitrogen in these soils, no significant difference among rotations, but on average, this 4 year rotation has slightly more nitrogen than the 2 year. And so what this means is that we actually detected a significant change in the carbon to nitrogen ratio of soils, essentially slightly lower values, but significantly so in this 4 year rotation. And so the implication really is that these rotations are changing the fundamental chemistry of the organic matter because most of this, the large majority of this nitrogen is bound up in the soiled organic matter. We'll come back to that in a second. Okay, so that's the story for the carbon stocks. Not much going on, but from a perspective of crop production, more than just the stock of carbon and nitrogen, we're really interested in the turnover, right? So how are these organic materials decomposing, and could there be differences there among these rotations, right? We care about this because decomposition of organic matter is tightly linked to processes we care about, such as nitrogen mineralization, right? Which is a major source of nitrogen to the crops in these diversified rotations. So to get at these decomposition dynamics, we built this apparatus in the lab to measure the CO2 being emitted from these cores. So we took some additional intact soil cores and incubated them in the lab for a year using this automated apparatus to get a good handle on how much carbon was decomposed from these soils and how it might vary among the cropping systems. And so here is this cumulative decomposition of organic matter to CO2. And what you notice over this more than year-long incubation is that these diversified systems have much greater decomposition on average, about 37% greater CO2 production in the 4-year rotation relative to the 2-year rotation. So this is interesting, although you might say, well, Stephen, right, we know there are more roots in these diversified rotations, so this is just the root residues decomposing. And it turns out the story is actually a little more interesting than that. We actually have some evidence that these diversified rotations are increasing the decomposition of older carbon in the soil that was actually months to years older than these recent residues. And we can infer this by making some additional measurements of the stable isotopes of carbon. And so you might remember from maybe high school chemistry class, if you look at the periodic table, carbon has an atomic mass of 12.01. And what this means, right, most carbon has an atomic mass of 12, but about 1 out of every 100 carbon atoms has a mass of 13. And this is, we can sort of ignore this in most cases, but it turns out plants actually have a preference for these different carbon isotopes. And different groups of plants will have different isotope ratios of the carbon that they take up into their biomass. And it turns out that warm season grasses like corn, which are known as C4 plants, have a characteristically different isotope ratio than most other plants known as C3 plants in our region. And so what we can do is use these isotopes to understand the inputs and the outputs of carbon from these systems. And we can actually ask the microbes what they ate, essentially, like how much of their diet is coming from carbon derived from corn, a C4 plant, versus everything else, the C3 plants. So again, we can come back to our incubations, right? Not only are we able to measure the amount of CO2 that's produced, but we can also measure these stable isotope ratios. So don't worry about these numbers. We kind of use a funny notation for these isotope measurements. These negative numbers are relative to a standard that's not really relevant for this talk. The key point is that these rotations are differing in the isotopes of carbon that's being decomposed. The 2-year rotation turns out to look very much like the isotope signature of corn, and we expect this because corn is grown every other year in this 2-year rotation. Whereas in these 3- and 4-year rotations, right, we're growing oats and clover, or oats and alfalfa. These are C3 plants that are changing the isotope ratio of decomposed CO2. So we can do some simple math, and we can use both of these data sets to calculate how much carbon came from C3 plants. So you can see here, there's more than twice as much decomposition from C3 plants in these extended rotations, which again is what we would expect, right? We're growing these C3 plants more frequently, and so it's those roots that are decomposing in this system. What was really much more interesting from our standpoint is that all of these rotations are decomposing a similar amount of carbon that's derived from C4 plants. So the most recent C4 plant that's been grown in this system has been corn. And so, right, if you compare the 4-year and the 2-year rotation, corn has grown half as much, right? Yet it's decomposing a similar amount of the C4 carbon. So just by mass balance, right, we've got lower inputs and higher outputs. This tells us we must be decomposing an older source of C4 carbon that's accounting for this increased decomposition. And moreover, right, we know that the overall stock of carbon in the soil hasn't really changed. And so those increased losses must be offset, right, by these greater inputs of new C3 carbon. Okay, so this is a little bit of a mouthful, but we can actually demonstrate this again using these isotope measurements of carbon in soil organic matter. And coming back to that figure I showed you a couple minutes ago, right? These are the bars are the amount of carbon. These circles are the isotope ratios of that carbon. And we can see a pretty big shift in these diversified cropping systems. Again, this is evidence that this carbon has been replaced. We've lost some of this older C4 carbon. We're getting more new C3 carbon from these diversified rotations. So what does this mean, right? I think the key take home with respect to farm management and climate policy, right, is that increases in carbon inputs can be offset by increases in decomposition. And the key point, right, I think we love to just manage soils as buckets for carbon, right? We're going to grow more plants. We're going to store more carbon. It's going to persist in soil. It'll be sequestered for long periods of time. That's sort of the assumption of these climate programs. But we know soils don't really work right like that, right? These are complex adaptive systems where we can turn one lever and we may be turning another lever as well. Okay. So coming back to this overall framework, right, of market-based approaches for climate, I think we need to think really carefully about how these different practices are actually impacting carbon stocks, but what the potential knock-on benefits might be, right? We might not necessarily get reliable benefits for carbon change, but we might have a lot of leverage with respect to nitrogen. And so that's where I'm going to pivot next. And so we know, right, nitrogen mineralization is one of the key benefits that organic matter decomposition gives us in cropping systems, right? And so, we can define nitrogen mineralization, right? Recall that most of the nitrogen in the soil is bound up in soil organic matter and crop residues. So the release of nitrogen as ammonium during decomposition, we define this as nitrogen mineralization. Some of that ammonium may be nitrified to nitrate. And so we can measure soils at the beginning of an experiment, at the end of the experiment, or over time in the field, right? We can compare the change in that ammonium and nitrate pool size. We define that change as net nitrogen mineralization. Okay, so we did this in our lab incubation experiment. This is useful, right? Because we've sort of simplified our system. We don't have any nitrate leaching. We don't have any crop uptake. So we can bound the maximum amount of nitrogen that might have been mineralized sort of under ideal environmental circumstances and compare that among these systems. And so what we find, right, is maybe not surprising, right? These are, Iowa mollisols with lots of organic matter, lots of nitrogen. They're mineralizing on the order of 200 pounds of N per acre, reporting this hopefully in units that are more useful for the agronomists. What's more exciting, perhaps, is that these 3-year rotations have this sustained boost in nitrogen mineralization. It's not just a boost after the 3rd year of the rotation, where we might expect a larger nitrogen credit from the red clover, but it's sustained across all phases of the rotation. That's really consistent with this overall increase of decomposition of slower cycling organic matter. And finally, in the 4-year rotation, we see an even larger boost from the alfalfa phase, right, which you might expect, right? We know that alfalfa can give us a nitrogen credit. And so you can compare this 2-year system with the 4-year, and there's over a 200-pound N difference of the nitrogen that's mineralized. Again, this is the whole profile soil nitrogen that's measured in these cores from the surface to 1 meter depth, although most of that nitrogen mineralization is occurring in the topsoil. Okay, so what does this mean, right? And so this is helping explain, the finding that we can dramatically decrease synthetic nitrogen inputs to these systems, right? With the slower cycling release of nitrogen from manure, the slower cycling release of nitrogen from legume residues, and the overall increase in organic matter turnover, right? We're able to supply a lot of nitrogen across all phases of these cropping systems. right? And so that brings us back to this table. So you'll also notice, in addition to these various cropping system practices, nitrogen management shows up in many places, right? And we know that we can get some fairly reliable climate benefits simply from backing off on our rates of synthetic nitrogen inputs. And this is because, right, many of you are aware of the importance of nitrous oxide. And so for those that aren't, nitrous oxide is a potent greenhouse gas that's produced by microorganisms in soils. And all else equal, nitrogen fertilizer rate is oftentimes the strongest predictor of N2O emissions, whether you're looking at different kinds of cropping systems or changes in management within a system. And in our region, in the Midwestern United States, on average, N2O emissions account for anywhere from about 1 to 4% of nitrogen inputs. There's a lot of variation depending on weather during a particular year, drainage class, other management factors. But so not huge from an agronomic perspective, but huge from a climate perspective. We can calculate these relative impacts of nitrous oxide versus changes in carbon by expressing that N2O and carbon on similar metrics. So carbon dioxide equivalents. It turns out that N2O is about 300 times more effective at warming the atmosphere than CO2 is on a mass basis. And so we can compare potential climate benefits, perhaps from adopting cover crops or from decreasing tillage. On average, right, there's tremendous variability among sites, but on average, you might get about 1,000 kilograms of CO2 equivalents per hectare per year. Even more, right, if we think about systems where we're not only increasing carbon inputs, but also really dramatically decreasing disturbance, things like prairie restoration. Although, unfortunately, when we compare this to N2O, the math is not in our favor. Sort of business as usual N2O emissions from typical central Iowa corn and soybean systems are on the order of, three times as much as we typically get from these optimistic carbon gains from cover crops and decreased tillage. So what can we do about this, right? Well, the simplest answer, which is, a challenge, right, is we know that relatively small decreases in the nitrogen rates can actually have an appreciable impact on nitrous oxide. And the benefit here is that these changes can be nonlinear, right? Small changes in nitrogen management may have a disproportionate impact on nitrous oxide, just like they do for nitrate leaching, for example. And the important point is that if we take, the assumptions that I stipulated on the last slide, it may actually see similar climate benefits from small N rate reductions as we do from average carbon gains from cover crops and no-till. Okay, so that's one point. The second point is if we think about these diversified rotations where we have impacts to really, back off on synthetic nitrogen rates even further, we may have larger climate impacts, right? All else equal, these legume and manure nitrogen sources are typically associated with lower nitrogen or nitrous oxide emissions, right? There are some exceptions. The context matters. More data is needed, but all else equal, this nitrogen is going to be less vulnerable to loss as nitrous oxide. The other point is that these avoided nitrous oxide emissions are likely to be more durable from a climate perspective than changes in carbon. So if we emit nitrous oxide today, we're stuck with it in the atmosphere for 100 years, right? That's the lifetime before that nitrous oxide is eventually zapped by ultraviolet radiation and degraded. Whereas carbon, right, we might adopt changes in cropping systems that lead to increased storage of carbon and organic matter. That's great. Unfortunately, it's reversible, right? All else equal, as the planet warms, we're increasing decomposition rates. We might have changes in management practices, right? We may lose that carbon back after a period of years or decades. So I think that's an important fact to consider. These gains from decreased nitrogen inputs may actually be more reliable over the long term. So the key point here, right, even though these diversified systems don't necessarily gain carbon and soil organic matter, we may have a larger climate benefit due to decreased nitrous oxide emissions. Okay. Just going to check my time quick. Okay, I don't want to go too far over. I'm going to briefly touch on some data that's hot off the presses here from the Cobb's experiment. Can't resist showing this. So again, many of you may be familiar with this long-term Iowa State University experiment established in 2008 to compare these different candidate bioenergy systems. So there's sort of a typical corn and soybean system managed for grain. That's the control. And then we have two continuous corn systems with about 50% stover removal. One of these is managed with a cover crop. We also have two different prairie treatments, so a low fertility prairie and then a prairie that's fertilized with nitrogen every year. Again, this is a rigorous randomized complete block design experiment located in central Iowa near Ames. Okay, we did a similar kind of soil sampling in fall of 2022. And again, we're measuring carbon down to a meter depth. And so what was really striking here, we did see some overall effects of cropping systems on soil organic carbon stocks. So these bars are the total organic carbon stock down to 1 meter, but really a counterintuitive pattern. And you'll note that the prairie, so the P bar here is the low fertility prairie, and the cover cropped corn system actually have the lowest carbon of all the treatments. And this had us scratching our heads. This is the result of a large collaborative team. And we got to thinking, well, is there some confounding factor here that's influencing the results? So thankfully, right, there's a lot of information available from this site. We have some soil maps, right? We take these with a grain of salt, but we can immediately see that these soils are variable at the Cobb site, as they are most everywhere. And what we found actually when we went and measured the particle size or the soil texture in all of these different plots, we find there are actually differences among the cropping systems. So it turns out this is sand content on the x-axis and the depth of the soil samples on the Y. What you'll notice is that the prairie and the cover cropped corn tend to have higher sand content, especially in the surface soils. And this is really unfortunate, right? Because we know that greater sand content correlates with lower organic matter content. We know those fine particles are important for protecting organic matter from decomposition. So this is really, as best as we can say, this is really bad luck in terms of the experimental design, right? This is a rigorous randomized design, yet by chance, we managed to pick up a statistically significant difference in shallow soil particle size. And really what this suggests is that these differences in soil texture are controlled by the differences in soil carbon are controlled by differences in soil texture and not by the cropping systems themselves. So it's not really that these prairies are losing carbon, right? We have good evidence that there's lots of root biomass. You can go look at the soils. You can see all the fine roots that are getting pumped into these soils. They just happen to be a little bit sandier than the others, and so they have lower carbon on average. And so really the cautionary tale here is that it can be very difficult to detect effects of practices on carbon, even in one of these rigorous long-term experiments. And so I think, when we think more about expanding measurements to farmer fields, these kinds of cautions are really important to consider. However, right, coming back to the impacts of organic matter cycling, there can be key benefits from these cover cropped and perennial systems, even though we don't see any change in soil carbon. So these are some old data by this point from Dye et al. At 2015, but demonstrating large reductions in nitrate leaching, both under these perennial prairie systems, as well in many years in the cover cropped corn system, which is this green triangle. So the cover crop corn decreases nitrate a little bit, the perennials decrease it a lot, right? So the key point, just by having roots out there longer, even if they're decomposing, they can play some really crucial environmental roles in these cropping systems. Okay, so take-home points. I hope I've convinced you that just increasing the diversity or the quantity of the plant carbon inputs to soils is not necessarily sufficient to increase the amount of soil carbon, right? I think that's a really key point we need to consider when we're thinking about, climate policy and practices. The second point, though, it's sort of the corollary, is that even when carbon doesn't change, there could be tremendous environmental benefits from thinking about these diversified rotations and perennial systems in terms of decreased input requirements, knock-on benefits for water quality, and decreased emissions of nitrous oxide. And I think from my perspective, it's suggesting maybe we might think about reframing the issue, right? In many cases, we might actually achieve greater environmental impacts by focusing on processes to increase nitrogen use, efficiency, and retention, as opposed to focusing primarily on soil carbon. The good news is that a lot of these practices are the same, right? Cover crops can help us hold on to some nitrogen. They might help us build carbon, maybe yes, maybe no, right? But if we have a more holistic assessment of these benefits, we might be able to be clearer-eyed about our practices and what we expect. So again, I'd like to thank all of the collaborators that contributed to this work and our funders, and look forward to a discussion with you all.
Yeah, so if you have any questions for Stephen, go ahead and continue to put those into the chat. If you're watching today, to get your CCA credit, go ahead and email Elena Whitaker at alenaw@iastate.edu by 5 o'clock today with your name, the name you entered the webinar with, and your CCA number. You can flip to the next slide.
Yeah.
So if you've not taken our voluntary demographic survey, please go ahead and do that. You only need to do it once for 2024. So if you've already done that survey this year, no need to do it again. And then next week, we are going to be having our 300th webinar. So I urge you to go ahead and attend that webinar. We're going to have Dr. Rick Cruz, and he is going to speak about soil conservation and water management and the keys to improving climate resilience. So go ahead, please attend that webinar next week. So we have gotten quite a few questions in over the presentation. So Stephen, is there any comparisons going on between raw manure compared to like traditionally treated manure, composted manure? Is there any comparisons being?
Absolutely. That's a great question. The devil really is in the details. And I assume the question is with respect to nitrous oxide emissions. And yeah, the context really matters, like the water content of the manure, the nitrogen content, how fast that nitrogen is mineralized, all of those can have an impact. Like I'm aware of some studies that, broadcast large amounts of liquid manure. You can get a lot of nitrous oxide from those events. So I don't want to, paint with too broad a brush about, the impacts versus synthetic fertilizer. But strategically used, right, in certain cases, there's good evidence that we can decrease nitrous oxide emissions from using legumes or manure-based sources as opposed to synthetic nitrogen.
Great. Somebody asked if there's any data comparing these results to like a biodiverse prairie remnant. And
yeah, absolutely. Yeah. So so with respect to like comparing the bioenergy prairies versus sort of prairies managed without biomass removal, maybe, ideally with grazers. Absolutely. And I actually included some of those data when I was talking about these sort of, optimistic carbon gains, right? This is a nice study here in Northern Illinois, like a really rigorous examination of changes in carbon in restored prairies over time. They measured about 1,600 kilograms of CO2 equivalent per hectare per year. So you can absolutely, you can gain soil carbon in a prairie. It can be larger than, is typically observed under, practices like cover crops or decreased tillage in croplands. The key point, though, that we're trying to highlight here is that simply having, perennial roots and increasing root production on its own is not necessarily sufficient to build carbon, especially if you've got biomass removal, as was the case with the Cobb's experiment.
So somebody asked, so with this extended rotation system, would this help reduce the need for all kinds of nitrogen, like manure, other forms of fertilizer other than just synthetic nitrogen?
Well, yeah, that's a great question. And so, right, you can manage these systems in different ways. The way this particular experiment has been managed, right, is to sort of simulate these integrated crop livestock systems that you would ideally have, right? Where you're generating forages or small grains, feeding those to livestock, and then returning the manure back to these fields. And so essentially that's how they've been managed. So we're getting a fair chunk of nitrogen in this manure. The assumption, though, is that it's going to be mineralized more slowly, potentially used with greater efficiency by the crops, thereby enabling us, right, to take more of the nitrogen credit in lowering the synthetic nitrogen use, right? You could imagine managing nitrogen different ways in these systems according to the particular characteristics of the individual farm operation. So hopefully maybe that touched on the question.
Um, so does the Marsden study take into account variable amounts of rainfall each year or year to year?
So it was, I guess, from which standpoint? So in terms of nitrogen management, right? This is being done by the ISU extension guidelines, the late spring soil nitrate test, and that integrates differences in rainfall, right, to the extent that they would impact nitrogen mineralization and nitrification and leaching. So it's that measure sort of integrates that. Right, it integrates the recent history that those soils have experienced, which are producing the amount of nitrate that's measured in that test. So I guess that's as good of a response maybe as I could do. Ideally, right, we'd have great weather forecasting so we could better predict into the future how much nitrogen might actually be mineralized. Unfortunately, we're not there yet.
Yeah, and this question kind of goes off that one too. Somebody asked if or how much carbon is lost via water throughput. So how much water is moving through, say, a
That's
diversified system compared to just a two crop rotation.
That's a great question. And so various researchers have measured what we call dissolved organic carbon. And so that's the movement of organic carbon through soil. And it tends to be very low in these systems. And one of the key points is that these are, high silt and clay content systems. And those mineral surfaces are great at binding with dissolved organic carbon. So typically, you can measure it, but it's essentially a rounding error in the overall carbon budget. But that's a good question. And that gets back to some of the broader environmental benefits of these diversified systems. So Marshall McDaniel and Matt Lieben and colleagues have measured a number of different beneficial changes in infiltration and aggregation, et cetera. And so we might expect more, infiltration of water through these soils, but it's not necessarily going to leach out more carbon through the system.
So yeah, somebody asked for both studies. Did you look at soil organic carbon and nitrogen mineralization over multiple years?
Yeah, so that's a great question. So what we did in this study is we incubated these soils in the lab. And sort of the reason we did that, right, is that if you measure the CO2 flux in the field, it's very difficult to interpret what that actually means because a lot of that CO2 is coming from the plant roots. So the roots breathe, right, just like we do, and they emit CO2. So you have to be able to separate the CO2 that's coming from the living roots versus the soil. And that's one reason why we oftentimes do these incubations in the lab. Similarly, from the perspective of nitrogen, right, we're able to eliminate leaching and plant uptake and just identify how much of the nitrogen was mineralized overall. And so these are long-term incubations in the lab under controlled conditions, right? And you can, we fully admit that it's an artificial situation, but it allows us to really focus in on those differences among the cropping systems. And so we're really looking at the long-term impact of the differences of these soils, so the cumulative impact of management on these soils.
Great. So somebody asked about the 3 and 4 year rotations and how that affects like corn and soybean yields, as well
Yep.
as just the inputs needed for those.
Yeah, we talked about that. Maybe that person missed the first part. So essentially, right, we see a yield bump in the 3 and 4 year rotations for both the corn and the beans, right? And this is sort of commonly observed, these diversification effects. There's multiple underlying mechanisms, right? Changes in pathogen pressure, et cetera. So I won't get, there's been a fair amount of work by a number of ISU faculty on this question at the site. So the question was yields and then inputs, right? In terms of inputs, right? Nitrogen fertilizer, right, is the most salient in terms of costs, right? Decreased synthetic nitrogen input costs. because of those, 75 to 85% lower inputs over the course of the rotation.
So somebody asked, is there or do you have a good way of quantifying N2O emissions? They
Yeah,
mentioned
that's a
that there's
great
a lot of
question.
yeah, they mentioned that there's a lot of air associated with that. So
There is, but you can do it. And so, my group has worked on a number of different ways to approach that question. And it's you can use automated chamber systems like that we've developed and others have developed. You can use lots of manual chambers and frequent measurements. And right, there's no perfect way to do it, but you can get reasonably high quality measurements that hold up. If this person is interested, I can refer them to some of the relevant papers. So we have and I can, if someone wants to email me too, I'm happy to share more references. So my email is Steven, Steven.Hall, Hall at wisc.edu. And I would love, I'm sure, many of us would love to measure the N2O emissions directly from the Marsden Farm experiment. Not a trivial undertaking if you want to do it well. So yeah, we definitely need more work like that in the future. The good news, right? Simply from what we know, we can begin to bound sort of the magnitude of changes that we might expect in these systems.
great. Somebody asked also if you're doing some same work or similar work in Wisconsin. They
Yeah.
mentioned the WICST trials.
Yeah, the WICS, the Wisconsin Integrated Cropping Systems Trial. Yes, we were starting some work there in collaboration with the leaders of that experiment. So I think it's a really nice sort of counterpoint. And I didn't touch on this, but they've found some interesting patterns with respect to soil carbon, right? So they have a range of these simpler grain rotations compared with diversified extended rotations, and similar to the Marsden study, right? They're seeing no real differences in carbon among those treatments. So it's nice to see that this isn't likely to be a one-off finding, right? There's some consistent evidence in some other studies as well.
Yeah, somebody was also curious about how you controlled the temperature for soil in the lab.
Yep, absolutely, right. And so, good, maybe in an ideal world, right, we'd have a growth chamber where we're mimicking the diel courses over the seasons, right? Barring that, we pick a temperature and we hold it for the incubation, right? So 22 degrees Celsius is pretty common in the lab, right? And so really the question is, if we hold all else equal, right? How do these cropping systems differ in their processes, right? We're not trying to extrapolate these rates to the field. We're just trying to understand what sort of differences have emerged over the long-term management.
Yeah, so somebody asked how much of the synthetic nitrogen needed was due to manure and how much was um, kind of came from that diversified cropping system itself.
Yeah, that's a great question. So how much came from manure versus sort of the release of biologically fixed N through the legumes? Unfortunately, with the data we have, we can't directly test that. So I'm working with some ecosystem modelers. I was really hoping to share some of that data today, but just totally ran out of time that can better address those kinds of questions. The good news, we're able to use a few different mechanistic models and pick up the differences in nitrogen mineralization that we observed with our data. So I guess it's sort of unsatisfying answer, but both, right? We know it's got to be both due to the manure and the mineralization of the crop residues and the general stimulation of organic matter decomposition in the system.
And then somebody asked, did you reference any studies regarding infiltration or aggregate stability? Considering with like
Absolutely, and I didn't reference those, but the relevant paper is from Marshall McDaniel's group, and I'm forgetting the lead author, but there was a recent paper that they put out that evaluated a number of different soil health measures at that site. So if that person wants to email me, I can track down that paper. The beauty of being able to work here is that there's been so much other work done by a number of different researchers. So it's a powerful place to do these studies.
um, another question we got in, if temperature was held constant throughout the incubation, how do you think the results would change in full-size field conditions?
Yeah, so again, right, the point is to say all else equal, how do the rates of organic matter turnover vary among these different cropping systems, right? And so you can move temperature up and down, you can ratchet those rates, right? You cool off the soils, you slow down decomposition. You warm them up, you speed it up, right? And so all else equal, you wouldn't necessarily expect the rank order of those differences to vary systematically, right? We're picking sort of an intermediate value so we can actually begin to interrogate the impacts of the cropping systems on these fluxes. Again, we're not trying to extrapolate out, into field conditions and look at within and among year kind of variability.
Great. Well, that looks like all the questions we had come in. So thank you, Stephen, for a really great presentation. I urge everybody watching to go ahead and watch our webinar next week. That'll be our 300th webinar with Dr. Rick Cruz. So other than that, have a great day. Thank you again, Stephen, for helping us out today and presenting your
Thanks to you all.
information.
Great questions. Thanks, Mitch. See you later.
Yep.